Hey you guys, so today I'm going to go through and work several examples for you on everything we've covered so far so that you can go through and skip to the sections where you still had a few questions and go back and look at some examples and see if that helps you or not. Hopefully it'll give you a little bit more clarity about some of the things we've been talking about. I know it's hard when you're here some days and not here the other days and not here at all for a whole week, so I'm just going to put out a lot of examples for you and then you can go back and watch them and skip around, and I'll try and put timestamps down in the description for you so that you can go back and just skip to the sections that you want. So the first thing we're going to talk about, the first thing we talked about so far this year was, is something a function or not? All right, so we're going to look at what makes something a function or not. And I'm sorry about the glare here. I'm sitting underneath the light and there's not really anything I can do about that glare. So for something to be a function, the rule for it to be a function is that the x's do not repeat. Right? That's the rule for something to be a function, that x does not repeat. So what that means, if we're looking at a bunch of ordered pairs, one of the ways we look at those is in a chart or a map. So these would be your x values, and then over here you would have your y values. So if we had 1, 3, 4, and then 2, 5. For this to be a function, none of my x's can have two arrows coming off of them. It means I can't have more than one x being repeated. I can't have an x being repeated. So if I had 1 to 2 and 1 to 5, because there's two arrows coming off of that 1, this would not be the map of a function because that 1 is being repeated. If we had a list of ordered pairs, that would be 1, 2 and 1, 5. So because we have this 1 that's being repeated, that makes it not a function. For it to be a function, each x value can only go to one y value. So 1 could go to 2, 3 could go to 2, and 4 could go to 5. That's okay. So in our ordered pairs, we would have 1, 2, 3, 2, and 4, 5. But since we have different x's, 1, 3, 4, for our ordered pairs, that's fine because the x's aren't repeating themselves. So that would be a function. The other way we can talk about if something is a function or not is based on the graph. So let me pull out my graph real quick. Okay, so here I've got a graph and it's going to have a lot of glare on it. I'm sorry. So if we had a graph of a function that looked like this, okay, whatever function that is, it's just some random wave I drew. For it to be a function, the x's can't repeat. So these are the x values along this axis here. If the x is repeated, then you would see it on our graph because there would be a line down here and somewhere else on that same x value. So we use what we call a vertical line test, which means a graph represents a function if you can draw a line, a vertical line, at any point throughout the graph, and the vertical line would only cross the graph one time. That makes it a function. So in this case, I like to use my pencil or pen or whatever I have to test. If I move a vertical line along the graph, there's never a point where my line is going through 2 points at once. It's always only going through one spot. So like right here, it's going through the graph right there at that x value. Over here, it's only going through the graph right there. So that makes this the graph of a function. An example of something that would not be a function, if I had, let's see, if I had this graph, okay, whatever graph that is, if I had this graph, if I put a vertical line through a point in that graph, or through that graph, notice now my line is crossing in two spots. It's going through up here and down here. I can draw a vertical line, or mostly vertical. It's not exactly vertical, but I draw a vertical line and it's crossing the graph in two spots. So this graph would not be a function because of that. And sometimes you'll have some where in some parts of the graph the vertical line test makes it not a function, but if you look at other areas you would think that it could be. So for example, if we draw a vertical line through the end of this graph, it's only touching in the one spot. But for it to be a function, a vertical line can't ever cross in more than one spot. So because we can draw a vertical line somewhere on the graph and it crosses in more than one spot, that makes this not a function. So that's, is it a function or not? We just talked about that pretty briefly. The next thing we looked at as we worked through our first section was domain and range. All right, so we have domain, and domain is the set of all x values. All right, so when we're looking at a graph, this really, what it's asking us is how far left does it go, and how far right does the graph go. And then also we want to know, is there anywhere in the middle that we don't have the graph? Okay, so that's the domain. Then range is the other part we talked about, and the range is the set of all y values. So this means when we're looking at a graph, how far up does it go, and how far down does it go? So that's really what we're looking for when we're talking about domain and range. And we looked at 3 different ways to write domain and range, and I told you it's really up to you, whatever you want to pick for how you write your domain and range. But I'm going to show you a graph, and we're going to try and find the domain and range of it. So let's get a graph real quick. Okay, let's look at this graph. Okay, so this is an absolute value function because it's that V shape that we talk about with absolute value functions. And so to find the domain of the function, we want to know how far to the left is this graph going, and how far to the right is this graph going, and is there ever a spot in between where it's not continuing? Is there ever a spot where it breaks apart? So if we look, following our graph to the left, our graph is going to the left, going to the left, going to the left, and it will continue off of the edge of our paper. So because of that, we know that the domain of our graph, right down here, the domain of our graph starts at negative infinity. Okay, so it's starting all the way back at negative infinity. We can't ever find a point where this graph first begins to the left. It's continuing onward. So because of that, we say it starts at negative infinity, and we put a parenthesis around negative infinity because you can't ever actually touch negative infinity. There's never a point where our graph equals negative infinity. Negative infinity just means that it keeps going forever to the left. And then on the right, as we follow our graph to the right side, our graph again is continuing on to the right. It's still moving off the edge of our screen or off the edge of our paper. So because of that, we say it's going to positive infinity. So from negative infinity to positive infinity, and again we use that parenthesis around the infinity. We don't use a square bracket. I know that doesn't really look like a square or a parenthesis with my hand, but we use a parenthesis because again that just tells us it keeps going. It never stops. It keeps going. Square bracket versus parenthesis. So that would be our domain. You can also write this in a couple of different ways. Negative infinity to positive infinity means all numbers work in our domain. It means that you could plug in any x value and have a point on our graph. So because of that, our domain would be all real numbers, which is that R with the 2 lines on the side. So that would be our domain. We can also look at our range. So, and I know I'm going back and forth here. Our range is how far up and down our graph goes. Okay. So we want to know how far up is it going and how far down is it going. So if we follow our graph, if we look at how far up it's going, as we keep moving our hand up, as we keep following our graph, it continues on. As we keep going up, our graph is continuing up to infinity. So our range, I have to find somewhere to write this. So our range, we know is going to go up to infinity, but we need to know where it starts. So I started with the top. Normally I start at the bottom, but that's just because in this case it's easy to see that it's continuing upwards. But notice our graph doesn't continue downwards. If I keep trying to follow my graph, I get to the bottom right here, and then it starts going up again. So I have a smallest point on my graph, which is right here. That is the lowest point on my graph right there. So I need to know what y value that is, because with the range we're talking about y value. So we want to know how far low down this is. So since this is sitting on the x-axis, on the x-axis, the y value is always 0. If we had moved up or down any, then we could figure out the y just based on how far up or down we had moved. But since we're staying on the x-axis, since we stay on the x-axis, our y value here is 0. So when we talk about our range starts at 0 and goes to infinity. And notice this point at 0 is included in our graph. Our graph is touching that point and then moving on. So that's where we use that square bracket around our graph. Okay? So that's domain and range. Let's do another example. I'm sorry, I'm trying to squeeze the graph onto the screen. All right. So let's look at a new function. Okay. Let's look at this function. Okay? So this is some kind of square root function. If you go back and look at the graphs of your parent functions, this is some sort of square root function. We don't know exactly what it is. We don't know the equation, but we do need to find the domain and range. So again, domain, we're looking for how far left and how far right the graph goes. So as we move to the left, if we keep following our graph to the left, eventually we get to the point where it stops. So because there's a point where it stops, our domain is going to have a lower bound. So I'm going to put the domain up here. So for our domain, oh, I don't know that it's going to be parentheses actually. I'm going to leave that off. So for our domain, as we go to the left, our graph stops at this point, which is 1, 2, 3, 4, 5 to the left of the origin. So since it's 5 to the left of the origin, the x value for that point is -5. And then since our graph is actually at this point, it's touching this point, we know -5 is included in our domain, so we put a square bracket around it. Then as we move to the right, notice our graph is continuing forever to the right, it's never stopping. So because of that, our graph goes up to infinity, and we always put a parenthesis around infinity. We could write this in a different way. Notice for our x values, all of our x values are greater than or equal to -5. As we start at -5 and we move up to the right, so everything is either greater than or equal to -5. So we could say our domain is all real numbers x greater than or equal to -5. So that's just another way of writing it. And then, sorry, almost lost my marker. If we look at the range is how far up and down our graph goes. Okay, so how far down and how far up is our graph going for the range. So if we follow our graph downwards, so we can start from up here and come down, as we follow our graph down, we do stop at this point. So we need the y value for this point. We know the x value is -5, but that doesn't help us with the range. For the range, we need the y value. So for our range, at this point, the y value is how far up or down this point is from the origin. So since we're still on the x-axis, we haven't moved that point up or down any, our y value is 0. And since the graph is actually at this point, it's touching that point, we put a bracket around 0. And then we follow to see how far up our graph is going. So as I continue onward, my graph keeps going up. It looks like it's starting to kind of flatten out. That's mostly just my drawing skills. But it's actually continuing to increase even as it goes off of our screen. So because of that, we know it's going to go up to infinity. And we put a parenthesis around infinity. Okay? So the other way we could write this, if we're looking up and down, the lowest our graph gets is 0, and so every y value is either greater than, above 0, or equal to 0. So we could write our range as all real numbers, y is greater than or equal to 0. And make sure you're using x and y when you're talking about domain and range, because that's pretty important. Domain is the set of all x values, range is the set of all y values. Okay. So that was a couple of examples on domain and range, and that's something we'll come back to throughout the year. So don't stress if you're still a little shaky on it. We'll keep coming back to it. Right, next we looked at x and y intercepts. So we said the x-intercepts where the graph touches or crosses the x-axis. Touches or crosses x-axis. And then the opposite would, of course, be our y-intercept. So our y-intercept is where the graph touches or crosses the y-axis. Okay, so those are x and y intercepts. First, we're going to look at how to find those by looking at a graph, and then we're going to talk about how to look at those with an equation and do several examples. So let's look at the graph of a random function. Let's say we have the function, whatever that is. Okay, actually I'm going to fix it a little bit because I don't want us to try and do weird numbers. Okay, there we go. Just pretend like that's a nice, beautiful graph. Alright, so first we're looking for the x-intercepts. I always start with x-intercepts just because it's the first letter in the alphabet. It's not the first letter in the alphabet, but it comes before y in the alphabet. So for our x-intercepts, we're looking for anywhere our graph touches or crosses. So as I look at my x-axis, if I go across the axis, I see a point here, a point here, a point here, and a point here. So for my x-intercepts, I'm going to start all the way over to the left. You can pick whichever one you want. We need to know the coordinate for this point. We don't just need to know the x coordinate, we need to know the ordered pair that tells us where that point is, so the x and the y coordinate. So for the x coordinate, we need to know how far left we went. So we went 1, 2, 3, 4, 5, 6, so I lost count. 1, 2, 3, 4, 5, 6, 7, 8, 9 to the left. Sorry about my counting skills there. So 9 to the left means we're at -9. So that's the first number in our ordered pair. And then we also need to know what our y value is. And for x-intercepts, the y value is always 0. Because on the y-axis, x is always equal to 0. So it's always going to be 0. All right, next we've got this point, which is at -1, -2, -3, -4, -5, -6. So -6, 0. We have this point, which is at 1, 2, 3-ish. I'm going to say 3. At 3, 0. It's kind of hard to tell when I've drawn it in marker because it's really thick, so I'm going to say that's 3. And then this point over here, which is 1, 2, 3, 4, 5, 6, 7. So 7, 0 would be our x-intercept there. So this function had 4 x-intercepts, and you can have as many x-intercepts as possible. Theoretically, a graph can have a whole lot of x-intercepts. Whereas y-intercepts, a graph will always have one y-intercept. It can never have more than one y-intercept. We just talked about the vertical line test in this video. If you think about it, if I had a point right here on my graph as well, if I drew a vertical line, and look, it's handy, we've already got one through it, that's going through 2 points, which would make it not a function. So functions can only have one x-intercept, one y-intercept, because if not, then it wouldn't be a function. So one y-intercept could have multiple x-intercepts. And for this y-intercept, we need to know the x value and the y value. And I'm going to write y-intercepts up here just for the sake of space. So if we count left and right, our point didn't move any to the left or to the right. It's still on the y-axis. It's still in the center of the graph from left to right. So because of that, our x value is 0. And with a y-intercept, the x value is always 0. And then it's 1, 2, 3, 4, 5 up. So this y-intercept is going to be at 0, 5. So that's x and y-intercepts using the graph. Using the graph, most people don't have a lot of trouble trying to find x and y-intercepts, other than just remembering how to name an ordered pair, how to name a point using an ordered pair. But if I asked you to go and draw or circle all the intercepts, no big deal. You could do that. The other part that people have a hard time with x and y intercepts is finding them algebraically. So let's get rid of our definitions for a second and talk about how to find them algebraically. So to find an x-intercept algebraically, which means we're going to be solving a problem, to find the x-intercept, you make y equal 0. To find the y-intercept, you make x equal 0. So notice it's the opposite. For x, y is 0. For y, x is 0. And so that's how we find them algebraically. So let's look at an example of that. Let's look at the function f of x, and I switched to f of x because we've talked about function notation now, but we'll look at what that does to our x and y intercepts. So f of x equals 4x plus 16. All right, so we need to find the x and the y-intercept. So our rule for x is we change y to 0. And the reason I changed this to f of x is because I wanted you to see what happens. See, when we talk about functions and function notation, f of x is the same thing as y. So when we want to change y to 0 for the x-intercept, all that means is we're going to replace the f of x with 0. So 0 equals 4x plus 16. Then to get the x-intercept, we solve for x. So we got to get x by itself. So to do that, we subtract 16 first. 16 minus 16 is 0. And adding or subtracting 0 wouldn't change anything. So we leave that off. But 0 minus 16 is negative 16. And we bring down our 4x. And then to get x by itself, next we have to divide both sides by 4. All right, 4 divided by 4 is 1, so we would have 1x. And then negative 16 divided by 4 is negative 4. And so we get negative 4 equals x. Negative 4 equals x is not our x-intercept. Negative 4 equals x is a vertical line on a graph. It's an undefined function. So negative 4 equals x is not what we put for our x-intercept. Just like when we were looking at the graph, we always wrote it as an ordered pair. So up here, we write an ordered pair. We said the x-coordinate was negative 4. The y-coordinate comes from this. The y is equal to 0 for the x-intercept. So negative 4, 0 would be our x-intercept. Now, y-intercepts are always easier to find than x-intercepts because you're not solving, you're just simplifying. So for the y-intercept, we're going to make x equals 0 and solve for y, or in this case, we have f of x. So we get f of x equals, and I'm going to run out of space. Story of this class, I always run out of space trying to do problems. 4 times 0 plus 16, just squeezed in there. So then we simplify what's over here. So f of x equals 4 times 0 is 0, so we get 0 plus 16. And then 0 plus 16 is 16. So f of x equals 16. And remember, f of x is the same as y. So when we come up here for our y-intercept, our y-coordinate is 16 because that's what we found f of x was equal to. And then our x-coordinate comes from this right here. We plugged in 0 for x to find that value. So in our ordered pair, we plug in a 0. So that's x and y intercepts. Okay. After we talked about intercepts, we talked about increasing and decreasing functions. And this was one that really messed with a lot of people's heads. It always does, so don't freak out if it was something you got a little stuck on, because even to this day, I'll sometimes mix it up. But we're going to look at where a function's increasing and where it's decreasing. So let's draw a graph. Okay. Does that work? It kind of works. Sorry, I'm looking at where I've drawn the graph because I'm just kind of randomly drawing it. And actually, I don't want this arrow. All right, so to look for where a graph is increasing and decreasing, we're looking from left to right. So as we look for increasing and decreasing, we're going to be looking at our graph from left to right. And when we talk about left and right, we're talking about x-coordinates. And this is the part that trips up everybody. We're talking about where a function is going up and down for increasing and decreasing, but we describe it based on how far left and right it's going. And I know that doesn't make sense in your brain. You're talking about up and down, but having to describe it left and right. But when we talk about increasing and decreasing, we're going to describe those values, where it's increasing and where it's decreasing, using the x-coordinates. Okay, increasing and decreasing, describe the x-coordinates. So when we look at this graph, when we talk about increasing and decreasing, you can think back to Algebra 1 and think about slope. Increasing is like having a positive slope. It's like going uphill. Decreasing is like having a negative slope. It's like going downhill. So as we look at this graph, we want to see as we go from left to right, where is it going down and where is it going up? Sometimes you can think about yourself being on a roller coaster. If you were on a roller coaster, where would you be going down, throwing your hands in the air, and where would you be, riding up the roller coaster, clicking along up the track? So as we go from left to right, our graph is going down when we first start. So I'm going to color code that to help me out. It starts right here at this point. That's where it starts, and it keeps going all the way until this point right here. So for this section of our graph, from this point to this point, we're going down. So we are decreasing. And I'm going to just label each part of the graph, then we're going to go back and describe those intervals. So our first section, we're decreasing. Hang on, I've got to get a sip of water. Next, as we continue along our graph, we start to go uphill. We start to slope up. So we're going to be increasing, starting at this same point and going up to right here before our graph starts to change again. So from this point to this point, our graph is going up, so we are increasing. And notice as I'm following my graph, I'm starting on the left and going to the right. Because if I did it backwards, if I started on the right and went to the left, it would all look different. So starting on the left, going to the right, we are increasing now. And then when we get to this point, our graph is going to change again. So I'm going to try and find a new color. There we go, haven't used green. And so our graph is changing again. It starts here. And then as we follow our graph, it's like we're slowly coming over this hill and falling down. So as we come down, we are decreasing. But notice this time there's an arrow at the end of our graph. So it doesn't stop decreasing right here. It's continuing to go down forever. Okay? So it's decreasing from this point onwards. So we're going to say it's decreasing. So we've labeled each section of our graph. We have our first section here, our second section, and finally our last section all the way over here. So we've labeled each section of our graph as decreasing or increasing, but we actually, in math, we give the interval to describe that point. Bell ringing. Okay, we give the interval to describe that point. So starting with our decreasing sections. All right, so notice over here, we started decreasing at this point and went to this point. We need the x coordinates of those points. We don't need the y coordinates. We need the x coordinates because the x's are unique in a function. Remember, x's can't repeat. Y values can repeat. So we can't use y values to talk about this because at one point the y value may be doing one thing, at another point it may be doing something else because y's can repeat. X's cannot repeat. So whatever the x value is doing at one point, it is only doing on that section. So x values, I'm just going to keep saying it at you. So we need to know the x coordinate for this point. So this point is, I'm going to come down here to my x-axis to look at it. So if I follow this down, we want to know what that x value is. So that is -1, -2, -3, -4, -5, -6, -7, -8, -9. Okay? So we start decreasing at -9. And we always put a parenthesis around it because we're increasing from this point to this point. We can't say that at -9 we're increasing. If I just look at this point and not the rest of the graph, you can't tell me that that point is increasing or that point is decreasing. A point just sits there. It does absolutely nothing without the rest of the graph. So we start at -9 and then we go until this point right here, which I did not do a great job of trying to place it on an exact x value. So if we follow it up, it's right here in between those two marks. Hopefully you can see that through the glare. So we need to know the x coordinate for that point. So if we count over, we are -1, little less than -2, about halfway between -1 and -2. So that would be about -1.5. So from -9 to -1.5, we were decreasing. And notice, for me to find the interval, I actually put a mark on the x-axis to help me see where that was happening. Because sometimes when I'm looking down at this point, I'll mix myself up in my head and start looking at the y's instead of at the x's. So if I bring the point up here, I know to look at the x's. All right, and then let's look at increasing because that was our next section. So when we describe our increasing, I'm going to bring it up here just for the sake of space. Okay, we were increasing from this point right here to this point right here. Well, this point right here is in that same spot. So notice sometimes you can be decreasing up to this point and then switch. So that same point is where our new interval will start. So from negative 1.5 up to this point, we are increasing. So we need to know the x value for this point. So again, I'm going to bring it down to right here on my graph so that I can find the x value easier. So this point is 1, 2, 3 over. So the x value here is 3. So from negative 1.5 to 3, so from this spot to this spot, our graph is increasing. So that section right there. And then finally, we have another decreasing spot. So again, starting at this point, which we just found was 3, so that's where our decreasing interval is going to start. So starting at 3, and I know I didn't draw it well so it might look like it's increasing here. That's meant to slope down the whole way. But from this point all the way down and continuing on, we are decreasing. So we know that this x value right here is 3. And then we need to go all the way over to the right and figure out what the x value would be all the way over here. So all the way over here, as we keep going off the edge of our screen, or off the edge of our paper, we're going to positive infinity. So from 3 to infinity, we are decreasing. Our graph is going to keep going down as we go off to the right, off to the side of our paper. Okay, so that's increasing and decreasing. Big thing there is just remembering to use the x values to describe where you're increasing and where you're decreasing. Okay. Next thing we talked about were the parent functions, and I'm just going to draw these really quick and name them in case you missed it. So in Algebra 2, we talked about a lot of parent functions, and the parent functions are just the most basic functions. These are ones we have on our word wall in class, and they are the ones that they're on our virtual word wall in Google Classroom if you ever need to go back and reference it. But these are the functions we're going to talk about throughout the year, but you have to be able to recognize their graph, know their equation, and know the name of the function. Those are the 3 things. So we talk about the constant function and the linear function, but those are functions that are covered pretty extensively in Algebra 1, so we don't really hit those very hard at all here. So you can go back and look at the word wall if you still need to reference those. But after that, we start with our next function, which is this one. Okay? This function is the absolute value function. Okay, so you need to know this graph, the V-shaped graph, is always absolute value. It doesn't matter if it's facing like this, which is the parent function, or if it's been transformed by shifting right or up or down or flipped over. If it's a V, it's the absolute value function. And the absolute value function's equation is f of x equals, or y equals, the absolute value of x. And for the absolute value, we use these 2 vertical bars on either side. Okay, so this is the absolute value function. After absolute value, we look at quadratic functions. Okay, so next is the quadratic function. The quadratic function's equation is f of x equals x squared. And the graph of the quadratic function looks like the letter U. And I'm actually going to mark the points on my graph because I just know where those points are because I want it to be the right curve. But this is the quadratic function. It's the letter U. So the absolute value function is a V, quadratic curve, so it's the letter U. So f of x equals x squared is quadratic. And again, the graph can be changed. It's still quadratic, but the parent function is f of x equals x squared, and the graph is this graph right here. So that's our quadratic function. After we talk about quadratics, we talk about the square root function. So the square root function is the opposite of the quadratic function. So it looks like, let me give some points to myself. Okay, that is the square root function. Okay, so we call this the square root function. Sometimes it'll be called a radical function instead, but this one specifically is square root because its equation is f of x is equal to the square root of x. Okay, so that is the square root function. F of x equals the square root of x. Okay. Next, we talk about cubic functions. So I'm just going through this list of parent functions. All right, cubic functions have the equation f of x equals x cubed, so a power of 3. And their graph looks like this. I didn't really give myself space. But that's what their graph looks like. Let me draw that better. I'm sorry, y'all. I tried to fit the word functions in around the graph, and it didn't work out well. Okay, so that is roughly what the graph of the cubic function looks like. And it's an interesting shaped curve. It's kind of changes direction as it's curving, but that is the cubic function there. Next, the opposite of the cubic function is the cube root. Same way the opposite of the quadratic is square root, opposite of cubic is the cube root function. Okay, so I'm losing my pens. Okay, our cubic function is what we just saw. Next, we're looking at the cube root function. Okay, so the graph of the cube root function looks kind of like that. Again, I'm not the best at drawing. Let me try and do slightly better. Okay, that's the graph of our cube root function. And the equation for that is f of x, or y, equals the cube root of x. So it's like a square root, but with the little 3 right here in the index position. That's called a cube root. So that's the graph of the cube root function. And then after the cube root function, we're going to look at the rational function. The rational function is a really weird graph. So the rational function, I'm going to draw it first. Okay, the rational function looks like this. Okay, and again, I'm not the best at drawing it, but it gets really close to each of the axes, but it curves off so that it never actually goes across any of the axes. Right, and so this is called, again, the rational function. And the equation here is y equals 1 over x, or, sorry, I'm trying to use function notation. F of x equals 1 over x. Okay, that's the rational function. I think I gotta just shout this out for a second. When you did your parent function scavenger hunt, I saw somebody make this graph using 2 bananas, so a banana and a banana like that, and it was hilarious. I absolutely loved it, so I had to just shout that out really quickly. All of you guys did a great job with your scavenger hunt, and I was really impressed, but the bananas one just kind of stuck with me. Okay, after rational functions, we have exponential functions. So our exponential function, okay, the equation for this is f of x equals a times b to the power of x. And our graph looks something like this. And that'll change based on what numbers you plug in for a and b in the equation. But something like that, where it gets really close to the x-axis but doesn't cross it, and then quickly increases on the other side. Okay, so that, again, it's roughly what exponential function graph will look like. And then finally, the last function we talk about in Algebra 2 is called the logarithmic function. Logarithmic function. And when we get to that, we'll work on saying, exponential and logarithmic, because it's a mouthful to try and get it out. But the equation for the logarithmic function is f of x equals log base b of x. Okay, that's the equation for the logarithmic function, and I put the words in the wrong spot because that's where the graph goes. But this is, if I can draw it well, this is our logarithmic function. Okay? So it gets really close to the y-axis but doesn't cross over it, and then quickly increases on the other side. So that is the logarithmic function. And logarithmic functions and exponential functions are opposite of each other. And we'll look at that again later in the year. But that was the logarithmic function. So those are all of our parent functions. Those are the graphs I want you to be able to name. Some of them more than others. Like I know exponential and logarithmic look similar, but I want you to know absolute value. I want you to know quadratic, square root, all of those graphs, and know their names and their equations. Okay? So those were the parent functions. After parent functions, we talked about function notation. Okay, so let's look at function notation. And I know this was something that confused a lot of you, and it's okay, because it's new. You know, you're used to seeing y equals, and we're switching it up with f of x. So function notation is just changing y into f of x at its most basic form. So if you have the equation y equals 3x, and using function notation, instead we would do f of x equals 3x. Whatever the variable is, that's what goes in the parentheses. And then we use the letter f most often. You can use other letters though. A lot of times we'll use f, g, j, h, k. Like all those letters in the middle of the alphabet we use a lot. But f is the most common for function. But we say it's a function with respect to x. That's just telling us that x is the variable. That's what we're plugging into our equation to try and solve. Okay, so that is function notation. The big thing we look at with function notation is substituting other things into our function. So, for example, if we have f of x equals 3x plus 1, because x is in parentheses, that's what goes here for my variable. If I change it though, if I want to find f of x minus 2, because x minus 2 is here in the parentheses, this goes in the place of my variable. So I'm going to take x minus 2 and plug it in wherever I had a variable in my equation. So when I do that, I bring down the 3, but instead of x, I replace it with what was in parentheses. And I'm going to keep the parentheses with it. So I get 3 times x minus 2. So x minus 2 is now replacing my variable. So 3 times x minus 2, and then we have the plus 1 at the end. And then we can go through and we can simplify this a little bit. So we can use our distributive property, which tells us if we have a number in front of parentheses, that tells us we're multiplying. And when we multiply, if there's addition or subtraction in the parentheses, whatever was in front gets distributed to each thing in the parentheses. So we do 3 times x and get 3x. And 3 times 2 is negative 6. And then we bring down our plus 1. And then if we simplify a little more, negative 6 plus 1 is negative 5. So we get 3x minus 5. So 3x minus 5 would be f of x minus 2 based on this original equation. So the big thing is just being able to plug whatever's in parentheses in for x. So we can do it with other equations. We can do it with expressions like x minus 2. We can plug those in. We can also plug in numbers. So if I had f of x equals 2 times x cubed minus 8, 2 times x cubed minus 8. If I want to find f of 2, because 2 is in the parentheses, 2 is what I substituted in for my variable. So wherever I have an x, I replace that with the 2. So I bring down the first 2, and then in parentheses, I'm replacing x with 2. So instead of x cubed, replacing it with 2, I get 2 cubed, and then I bring down the minus 8. And then I can simplify this. So 2 cubed is 8, so I have 2 times 8 minus 8. And then 2 times 8 is 16, so I have 16 minus 8. And then 16 minus 8 is 8. So f of 2 is equal to 8. So what that actually tells us is that if we graphed this function, Where this function goes through the x value 2, the y value is 8. So if we looked at the graph of this function, we could find the point 2, 8 on the graph. So that's what this does for us. It's just a way of plugging in values. The same way if you had y equals 2x cubed minus 8 and you wanted to know find y when x equals 2. This is just another way of saying find y when x equals 2. So that's what we're doing here. We're just plugging something in for our variable. So that's the first part of function notation, is just being able to substitute something in for the variable. But what function notation also allows us to do is change things up a little bit more. So if we had the equation f of x equals 3x plus 5, I can do things besides just plugging something in for x. Okay? If I want to find f of x minus 4, I can do that. I know what f of x is. I'm just plugging something in. All right? It's just f of x is a variable in this situation. So I want to plug in something for f of x so I can simplify. So f of x up here, we said f of x was 3x plus 5. So I'm going to bring down 3x plus 5 and plug it in for f of x. So when I do that, I get f of x minus 4, so 3x plus 5 is f of x. Okay, that's f of x. And then minus 4. Okay? And then we simplify the right side. So we keep the 3x, and then 5 minus 4 is 1. So 3x plus 1. So that's what we're doing when it's not inside of the function notation. Okay, and that's some language I'll be using, a couple of words I'll be using a lot, inside the function versus outside the function. So when something's happening in the parentheses, I call that inside the function. When it's on the outside of the parentheses, that's outside of the function when we're using function notation. So that's going to be important when we talk about transformations later, inside versus outside the function. So say we had something like f of x equals the square root of x. Okay? That's a parent function right there, right? So if I want to know what is negative f of x plus 2, okay? Negative f of x plus 2. I've got two things happening here. Inside my function, I have x plus 2. So that means when it's in the function, it goes in place of x. Whatever's in the function replaces x. Whatever's outside of the function changes everything else. I don't know if I'm explaining that well. So when I do this, if I'm trying to rewrite a function, I like to break it down into two steps. First, I do the inside of the function. So first, I'm going to just find f of x plus 2. Then I'll worry about the negative. So f of x plus 2, inside the function, gets plugged into the function for x. So since there was an x in the square root, I'm going to change that. Instead of x in the square root, I'm just replacing it with x plus 2 in the square root. Okay? So that's just f of x plus 2. It's plugging whatever's in our function in for x, in for our variable. Next, we had negative f of x plus 2. So negative f of x plus 2 means we're going to bring down our function that we just found for f of x plus 2. So we bring down square root of x plus 2. The negative outside tells us we put a negative outside of the function, so out in front of our square root. And that's all that that negative does. It just goes out in front of the square root, and that's what changes about our function. So that's a problem where there was changes happening inside the function and outside of the function. Okay, let's look at another example. Let's look at a rational function. Let's look at, again, we're going to start with the parent function. F of x equals 1 over x. Okay? And say I want to find f of x minus 3 plus 2. Okay? Actually, I'm going to do f of negative x minus 3 plus 2. I'm throwing in another negative. So for this, again, what I do first is I find the inside of my function. Then I worry about whatever's outside. I first focus on what's inside. So negative x minus 3 is in the function, it's in the parentheses, so that changes our variable. So when I rewrite this, f of x, negative x minus 3 replaces the x. So instead of 1 over x, I get 1 over, and I'm plugging in negative x minus 3. 1 over negative x minus 3. So that's the f of negative x minus 3. Then we're going to add the plus 2 now, because that was on the outside. So f of negative x minus 3 plus 2. Well, we just found f of negative x minus 3, right? We just did that part up here. So we bring that part down where we have f of negative x minus 3. So we bring down 1 over negative x minus 3. And then the plus 2 over here is outside of our function. So it's going to go after the f of negative x minus 3. So just at the end of everything, we're going to add on a plus 2. So this would be our function, f of negative x minus 3 plus 2. And we'll look at next week, this function, all of the things we just did represent transformations on our function. So subtracting 3 does something, adding 2 outside does something, putting a negative inside the function does something. So that's why we're introducing it now and doing all these changes here so we can talk about it with graphs next week. Okay, so that is function notation. The next thing we talked about were transformations, and transformations are really hard to wrap your head around, and that's okay because we're just playing with them right now, just getting used to them. So we're going to go back to our handy dandy graph, and the glare is getting worse every second. So we're going to go back to our graph, and we're going to do some transformations on this function. So we're going to start with one of our parent functions. Okay, let's start with a quadratic. And it's probably going to be the worst drawn quadratic in history, but there we go. So this is our quadratic. What I want us to do is apply some transformations. We've got a list of transformations we can do. We can shift it horizontally, left or right. We can shift it vertically, up or down. We can reflect over the x-axis. We can reflect over the y-axis. And then the other two that we don't look at as much are stretches and shrinks. So we can stretch it horizontally or shrink it horizontally. We can stretch it vertically or shrink it vertically. So I like to think about playing with like silly putty. If we're stretching it, it's like we're pulling it apart. We're stretching it out. If we're shrinking, it's like we're squishing it, compacting it tighter. So if you had silly putty, it'd be like pulling it and stretching it out, or shrinking it would be like squishing it down into a ball. Okay, so that's what we talk about when we talk about stretches and shrinks. But we're not going to look at that as much. We're going to focus mostly on shifting left and right, up and down, and then our two reflections. So first we're going to transform this graph. Let's do some horizontal shifts. Okay, let's shift this. I'm sorry, I'm trying to spell and talk at the same time, and it's not going well. Okay, we're going to do a horizontal shift left 2. I mean, look, left. I meant to say left. Okay. So when we do our transformation, what I do is I pick points on the graph and transform those specific points rather than trying to move the entire graph. I move a couple of points and then connect the dots. So I know I've got a point right here. That's a pretty easy point for me to see. For me to do my horizontal shift left 2, I'm going to take this point and move it 1, 2 to the left. Okay? And that's just one point on my graph. I like to pick points that are at whole numbers, so 0, 0, this point's at 1, 1. I like to pick numbers like that rather than like picking something like this right here, which is kind of in between x values and in between y values, because that's going to be hard to shift left 3. It's going to be harder to count. So next, if I look at this point for reference, I want to move this point left 3. So starting here, I'm going to stay at the same height, same y value, and just move left. So 1, 2, oh, I'm just moving 2, sorry, left 2, not left 3. So I'm going to move 1, 2 to the left. Okay, so that's a new point on my graph. So that's part of my graph. I need something over the, notice my graph kind of has two sides. So I've done this side, I've transformed this point and this point. I need to transform something on this side. So let's do, I had a point here, but I kind of covered it up with my new one. So let's go up here to this point. Okay, and let's move this point 2 to the left. So 1, 2 to the left. Okay, so I'm going to go through and I'm just going to connect the dots. So I know that a quadratic is what I had initially, and that's a U-shaped curve. So I'm just going to kind of fill out that U. Okay, and I know I didn't draw my lines as long. Let me try and fix that. There we go. So notice it's the exact same graph. It just moved left 2 spaces, right? It'd be like, you know the cha-cha slide where they're like slide to the left, slide to the right. That's what it did. It just slid to the left 2 places. Okay, so it started over here and then slides to the left. All right, so that's a horizontal shift left 2. All right, so shifting left and right is probably one of the slightly easier ones to do, just because it's picking a point and moving it left and right. We can also move vertically. So say I had the graph of, let's do a weirder one. Let's do square root function. Okay, so here is our square root function, kind of roughly sketched out. And we want to, let's transform this one. Let's do a vertical shift. Let's go down 1, okay? Vertical shift down 1. So again, I'm going to take a point on my graph and I'm going to move it down 1 place. So this looks like an easy point for me to move, so I'm going to take this point and move down 1. And that's a point on my transformed graph, on my new graph. I've got a point here that I can move down, move it down 1. And then let's look, see if there are any other easy points. This point right here looks kind of easy to transform. So I'm going to move this point, oh, not there. I'm going to move it down 1, okay? Then I just connect all the dots to get my transformed function. Okay? So that would be a vertical shift down 1. So it just moved down a little bit. So those are vertical and horizontal shifts. It's moving left and right, up and down. The other 2 types of transformations I want us to be able to do by hand are reflections over the x-axis and reflections over the y-axis. Okay. So let's look at the graph of the cube root function actually. Let's look at that graph. Okay, so this is, again, kind of roughly the cube root function. It's not exact. I'm not a perfect sketch artist or anything. Okay, this side's pretty good. This side, I'm going to fix this side because it'll mess us up when we're transforming. Hang on. I apologize. I'm not an artist. Okay, that's a little bit better. That's more like what the cubic function is. So what I want us to do is I want us to take this function and reflect. That is nowhere close to how you spell reflect. Reflect across the x-axis. Okay, reflected across the x-axis. So this is right here is the x-axis. So I like to kind of draw myself a little symbol to let me know I'm going to be reflecting it. And when you reflect across the x-axis, it's like making a mirror image on the other side. So whatever you have up here, it should be like looking in a mirror. So like if you know how if you like hold up one hand to a mirror, it'll look like you've got both hands pressed up against it side by side because of the reflection. That's what's going to happen over here. We're going to get an identical copy of this part of the graph down below the x-axis. So to do that, we're still going to use reference points to move it. And when we reflect across the x-axis, we're moving down, right? It's kind of like a vertical shift, but not exactly. So our x values stay in the same spot, right? I'm not going to be taking this point and moving it like over here when I'm reflecting, when I'm basically flipping the graph down here. So all I'm going to do is change the y's. So this was at +1. My new point is going to be on the opposite side at -1. right? Let's go all the way over here. This point over here is at positive 3. On the other side, it's going to be down at negative 3. So it's at exactly opposite. And then this point was at 0. And it's at, when you reflect it, if it's on the axis, it doesn't move. Okay? So this is part of our graph. That's this half of our graph reflected over the x-axis. So notice, if I ignore this, these are mirror images of each other. They reflected across the x-axis to give us this part. Okay, then on the other side, we're going to do the same thing with some points. So this point, the y value is at negative 1. I'm going to flip it over to the other side and move it up to positive 1. And then, let's see, over here, this point is at negative 3. I'm going to flip it over and move it up to positive 3 for its y value. Okay, so just reflecting it over to the other side and making that mirror image. And when I connect the dots, I get my new graph. So in the red, we have the reflected across the x-axis version of the cube root function. Okay? So you can kind of see how they're exactly opposite of each other. So that's a reflection across the x-axis. And then let's look at a reflection across the y-axis. The first one I'm going to show you is going to be super weird, just for the sake of showing it to you. Okay, we're going to look at the absolute value function. And we're going to try and reflect this around the y-axis. Okay, so we're going to do reflect across the y-axis. When we go to reflect across the y-axis, again, I'm going to draw my little helpful hint to let me know which direction I'm going. I'm again going to pick reference points. And this time, when I'm reflecting across the y-axis, I'm starting, whatever's over here is going to come over to this side. Whatever's on this side is going to move over to that side. And I'm going to get a mirror image. Well, if you notice with our graph already looks like a mirror image of itself. It's symmetric, right? If you folded it in half, the two sides would meet up perfectly. So if we think about a reflection across an axis looks like a mirror image, right? It's a reflection, it's a mirror image. If our graph already looks like a mirror image of itself, it's a hint, things might look weird when we do the reflection, right? So let's just look at it. So I have this point right here. It's at 1, 1. When I do a reflection across the y-axis, I think I said x earlier, I'm going to do a reflection across the y-axis. I'm going to move this point over the y-axis the same distance. So if it's 1 over, since it's at positive 1 for the x value, it's going to now move to negative 1. But notice I moved this point to a point already on my graph. Let's try again. Now let's look at this point. This point is at 3, 3, so x is positive 3. If I reflect this over the y-axis, I'm going to move it over to negative 3, so all the way over here to negative 3. And this would work better if I was a better artist and had drawn my graph perfectly. But notice, again, this point it's supposed to be on my graph. Ignore the bad drawing. It's on my graph again. Okay, so that's kind of weird. Let's look at a point on this side, see what happens. Let's look at this point. This point is at 2, 2. And I'm going to reflect it across the y-axis. It's going to move this same distance across the y-axis. So if it was at, it's at negative 2, 2. I think I said 2, 2. It's at negative 2, 2. Since it was at negative 2, when we reflect across the y-axis, it's going to change to positive 2. And then our point that was at the origin is going to stay the same because it was already on the y-axis. So notice, if I connect these dots, the red is my transformed graph. And I kind of drew it off to the side so you can see it, but these lines should be directly on top of each other. When I did my reflection across the y-axis for this graph, it stayed exactly the same because I already had a mirror image. So when I reflect, I should get a mirror image in the other direction. Well, that's the same exact graph. So graphs like this one or the quadratic function that are already a mirror image, when you reflect them, they'll look the exact same. So because of that, that's not the best example. I just wanted to show it to you. Let's look at an example that would change when we reflected it across the y-axis. Okay, let's look at, what's a good graph to do this with? Let's look at the square root function. Okay, so this is our square root function, mostly, if I drew it better. Okay. Just ignore me trying to draw, you guys. All right, that's our square root function. And we are going to reflect it across the y-axis, okay? So reflect across the y-axis. So when we do this, this point that was already on the y-axis is going to stay where it is. We had a point over 1 at 1, 1. When we reflect across the y-axis, it's going to move to the opposite side of the y-axis, so it's going to move to the over left 1 from the axis. And this point was at 4, 2. So instead of being at positive 4, 2, when it reflects over the y-axis, it's going to go the opposite way. So instead of positive 4, we're going to come over here to negative 4, 2. And so then we get the graph of our function. So notice these are mirror images of each other. All right, they're exact opposites. So that would be the graph of the reflection across the y-axis for the square root function. Okay, so that was a little bit on transforming functions. I give you the transformation and then you transform the functions. The other thing I had you doing was looking at a graph and telling me what the transformations were. And this part's harder. So if I give you the graph of, let's see, if I give you this graph, you first have to be able to tell me what type of graph it is to be able to recognize the transformation. So that V shape is always indicating an absolute value function. Okay, so you need to remember what the original absolute value function looks like so you can know what the transformation has been. So that's why we started with talking about the parent functions and what they look like. So the original absolute value function looks like that, roughly. I'm just trying to sketch it out. So we want to know how this is moved. To know how it's moved, you don't have to use a lot of points. You just have to pick a couple and see how they moved. So I know that this point right here is the lowest point on my graph. It's where that vertex of the V is, the bottom point. So if I look at this graph, that has been moved over 1 and up 1. So we moved over 1, up 1. We moved specifically right 1, up 1. So if we move right, that's a horizontal shift. Right 1. Okay, so we moved right 1. And then we also moved up 1. So that is a vertical shift up 1. Okay, so we had a horizontal shift right 1 and a vertical shift right 1. Okay, let's look at another one. Okay. Again, not the best graph ever. Definitely not. But hopefully you can see this is a U-shaped curve. So U-shaped curves are quadratic functions. So the parent function for a quadratic function looks something like this. Okay? So we want to know how this graph has been transformed to get down here. Well, first thing you hopefully notice is that we've got an upward U and a downward U. It's kind of like a smiley face and a frowny face. All right? So to get to this point, our graph had to reflect. And since it's flipped downwards, it reflected over the x-axis. Okay, so that's the first transformation that happened. There was a reflection across the x-axis. Okay? But notice, it didn't just flip. It's also, this point right here is now kind of down and over. Okay, so let's look at this point. Okay, it was the lowest point on our original graph. Now it's the highest point on our new graph. But let's look at how that changed. So to go from here to here, we have to move down 1 and we have to move left 1. So when we write our transformations over here, if we move left 1, we had a horizontal shift. Left 1. And then we also had a vertical shift down 1. Okay, so those are function transformations. Okay, next week when we're back in person, we're going to talk about what those look like when you actually have the equations and not the graphs, because you can do this without the equation of a function, or sorry, without the graph of a function. You can do it based on just an equation. So that's what that experiment I had you doing with Desmos was about. So for anyone who's a little confused, I gave you 2 equations. So I may have given you like f of x equals x squared, and then I wanted you to find, I wanted you to also graph f of x equals x squared plus 2. And at the top it said f of x plus c, or something like that. I want you to go to Desmos on the link, type these 2 equations in, and look at their graphs, the same way we were just looking at graphs, and figure out what transformations happened. Did it move left? Did it move right? Did it move up? Did it move down? Did it reflect? Tell me what happened in those slides. And it doesn't have to be 100% right. I just want you experimenting and playing with these before we come back next week. So hopefully that clears up any questions you may have had. Let me know if there's still something you're confused on. If you have time to watch this video before our video call this afternoon, I am doing a video call, so you can come and ask me any questions you still have. All right, you guys, have a great day. Maybe.